Hi everyone.
Hello.
Yeah, it seems
Hello.
they use a new
Good evening, sir.
new Zoom
Yeah, I
environment.
noticed it was a different ID.
It's a little different, like.
Hmm.
I cannot see you. So I cannot find the sharing window.
Hmm?
How to share the? Maybe I.
Do you have a button at the bottom that says share screen?
Yeah, but
Or do you mean the share the link button?
I don't have the share button. With.
Hmm.
Hmm? Maybe I will get in. I mean I quit first. Hi everyone. Hello.
Yeah, we can hear you.
You can hear me, right?
Yeah.
Yeah, that's great. So probably today I think because next week we will have a final presentation. But you know next week is a holiday. Next Monday is a public
Hmm.
holiday. So but we already know that. So we ask you to prepare the video clip. But for different group, they have a different project, right? I think for team, your group is doing E, uh,
EEG, yeah.
EEG, right? And some
Hmm.
group doing ECG, and some group doing the IMU. So because I don't want to disturb too much for today, so I think we should more concentrate on the project. So we do our best to finish by next Monday, and then you can send it to me. And the worst case scenario is like because I extended the report to end of next week. So to you submit a report end of next week. And because I'm currently discuss with teaching deputy head of school, for our case, should we can we use the Saturday to discuss about uh, the video clip? Because we want to student can know each other groups work. There's two options. One is like we have a extra time. We find 1 hour. Maybe we quickly discuss about each video, or we can just like you submit the video, and then we reorganize a meeting during I mean the vacation time. But I will discuss with you all the options after the class during the group discussion. I'll be with you. So I think um, because this semester is really special, it's difficult to teach you hardware. So and also we our selection of project is limited by some equipment. So we provided a limited equipment, I mean project. But I still want to you learn as before as previous semester. So you can touch. Although you cannot touch this equipment, maybe we give you some hint, and also you can learn from other group members. So I will discuss it with you later. But today, the first topic is the 2D image processing. So this is a very important topic. Actually, it's a very natural extension from 1D signal to 2D signal. Why I said this is very natural, and because like you can directly thinking about from 1D. For example, 1D we have Fourier transform. We have discussed 1D Fourier transform, FFT. We actually have a 2D FFT and 2D Fourier transform. And I will show you what's the connection and what's the difference and how to explain 2D FFT, so the spectrum of 2D image. And then for the filtering, we already learned the filter, like for stationary signal, right? We can deal with by using a FIR, IIR filter. And for the 2D, we also can design high pass, low pass, and even some band pass filter. I will show you like use MATLAB. So MATLAB is a very powerful tool, and we can show you very soon. And also we will discuss wavelet. Actually, this topic should cover by 2 lectures, but even 2 lectures is not enough. So, but for the, like this subject, some students from postgrad subjects. So some students already know a lot. So there's a, but for bachelor student, maybe you never learn this, maybe have some difficulties. But my philosophy for teaching these subjects is not just teaching all of the contents. I'm just want to teach you the method of learning engineering related subjects. So first philosophy is we first teach you how to use software, for example MATLAB and LabVIEW, and we learn the abstract concept and knowledge by using software. So this is one of the philosophy. Another philosophy is like we just give you how to learn the subjects. You will see like in all of my slides and the things, I give you extra slides. Actually, I cannot cover all of the slides, but I provide in the Canvas. I hope you can read them in the future, or if you have time, because some students maybe only learn 1 or 2 subjects. Maybe you have more time to concentrate, so you can learn the videos. So basically, especially for the last stage, for the after non-stationary signal explanation, we start to concentrate on the application of signal processing. And I think I cannot cover all the application area. So, but today I still want to extend. Like if we not extend, we feel like our subject is not finished. So now we look at our go to the Canvas. I think I go Canvas. So here's the Canvas. We will discuss how to prepare the video later, but we go to the modulars. So we go to, you can see I put all the learning material, even lecture 10, maybe we never touch because there's no group select this project. So I will not discuss about week 10 contents. We only up to week 9. So week 9, week 8 and week 9, today we will discuss both. So I just want to teach you how to learn the signal processing in the future, because no subject select 2D image processing. But I still want to give some time to discuss with you. So the first is like 2D signal processing. So this is for normally they call the stationary signal. It's like 1D signal. So I put 3 video. One is for discrete time 2D transformation, and they have a MATLAB code as well, how to use MATLAB as well. So this one, I think this is from theoretical point of view, derived from 1D extended to 2D. So basically, if you can understand this video, you will be good in theory. So but this is not compulsory until unless you are very keen to learn the theory behind. So but you can see they are very straightforward.
And the thing to note is
first from 1D.
But the basic idea is exponential. And here, you know,
so it's from
this
1D
omega was continuous,
and then to 2D.
discrete.
2D is maybe is before is a one integration, now it's double integration or double summation. So you can see this one is very similar with 1D.
And just in the same way,
this
that there's a forward transform, there's also an inverse transform.
This 2D discrete
very simply
Fourier transform. And so this is one you can see as they have connection with 1D. So 2D Fourier transform you can consider, for example, first we do 1D.
Stephen.
Yeah.
Can you share your screen?
Oh, so I cannot. Oh, so you cannot see. Oh, sorry. Apologize. I thought you are seeing my screen. Apologize. That's sorry. So where's the?
Should be a green button at the bottom of the Zoom window.
This time the so you oh, okay. So oh, sorry, I think this time you changed the setting. Where's advanced? So they changed the setting. Okay, so can you see now? See my screen? Yep, that's great.
Now.
Sorry, because this time they changed the but I will put it to the YouTube. You can see what I'm talking. But here you can see this is a
you don't need to write.
This is one video. They're talking about 2D FFT. So there's 1D. You can see 2D can be considered as a 1D extension. So you can see this is 1D Fourier transform, and then you can do twice. So how to do that? For example, you have image, you have x-axis, you have y-axis. So do you know what's the difference between image and the for example the normal 1D signal? So in image, so you have a pixel. If digital image, you have pixel. So for each location, you have location is like x and y. You can define the location, right? And then there's a value called pixel. And then you can, if you is a colored one, you have RGB. So you can red, green, and blue. So you have 3 dimension. But for the black photo, you only have 1. So you have a pixel, and then you can it's actually just a number, right? Just a number and a value, and then you can do you can treat this one as first you can treat this 1D signal, right? For example, you only treat x is changing, y is fixed. For a fixed y, you can do x as changing, and then you can do the Fourier 1D Fourier transform, and then 1D DFT, and then you can do get the 1D one, you will get a complex because for each row you have long complex number, and then you do in the maybe I see another video, it's very good video, and then I think I put in the this morning I found a very good video.
Can care be better at home?
Someone from Medibank mentioned that there's a chance I can do rehab at home.
In this video, I'm going to explain the 2D Fourier transform.
So this is the voice is not good. It's low. That's why I didn't select. But there's some part is quite interesting.
That you've been learning is simple. The problem is interpreting the results of a 2D Fourier transform. And even more complicated is trying to predict what an image might look like based on its 2D FFT power spectrum. First, let me explain how pictures are represented on computers. When you have a picture like this, your computer represents this as a matrix. And the color in each little matrix element corresponds to a number. So in fact, the matrix looks like this. And you can see that larger numbers have darker colors. Now, when you have data organized in a matrix like this, the 2D FFT works by first taking a one-dimensional FFT along the columns of this matrix, and this produces a matrix of one-dimensional Fourier coefficients.
So you can see this is a one-dimensional Fourier coefficient. You can see you have a imaginary part. This is not just a real number. They have this is a complex number. And then they do complex 1D.
And that you can see in this image.
1D
frequency
FFT
is on the y-axis. The top row is the DC component. And all of these values are Fourier coefficients for the Fourier transform from each column. The next step is to perform a 1D FFT on the rows of this matrix. The result of this step is a two-dimensional matrix of Fourier coefficients. In this matrix, the low-frequency coefficients are around the edges and the corners, while the Nyquist is at the center of the matrix.
So this one is also this one is already 2D FFT already. 喂 ，Carry， 没有啊，你们都听不见了是吧？哦，那我这还看着可以啊。那行，那我赶快上一下。Hello. Hello.
Hello.
Are you okay this time?
Yep.
Okay. So sorry, I don't know why they just like make me out. So have you seen this video? I'm using this one. Have you start from here?
One-dimensional FFT along the columns of this matrix.
Hi, Carrie, have you seen this video?
I don't think so. We saw this video, sir.
Okay, in that case, let's start from start. This is a very interesting video, very good video. I just found this morning.
How pictures are represented on computers.
All right.
Yep.
When you have a picture like this, your computer represents this as a matrix. And the color in each little matrix element corresponds to a number. So in fact, the matrix looks like this. And you can see that larger numbers have darker colors. Now, when you have data organized in a matrix like this, the 2D FFT works by first taking a one-dimensional FFT along the columns of this matrix, and this produces a matrix of one-dimensional.
Hello, can you hear me?
Yeah.
And
can you hear me?
In this image.
Oh yeah, now it's okay, sir.
Now it's okay now.
The top row is the DC component.
Okay. So this is talking about I'm talking about the 2D FFT. So they first from 1D FFT.
The next step is to perform
from column, and then they do after the column you can get you can see the complex number. actually is the coefficients of of a Fourier transform, and then they do a row Fourier transform for the complex number, so they get another
from a 1D FFT on the rows of this matrix. The result of this step is a two-dimensional matrix of Fourier coefficients. In this matrix, the low-frequency coefficients are around the edges and the corners, while the Nyquist is at the center of the matrix.
So this also needed to do shift. So currently still, I mean, normally for the normal one is like in the center is the low frequency, in the corner is the high frequency, but this is haven't shift yet, so they do shift.
You'll recall that in a previous video, I showed that in some disciplines, people show the 1D power spectrum with DC in the middle, negative frequencies on the left, and positive frequencies on the right. For images, shifting the coefficients so that the Nyquist frequency is at the edge and the low frequencies are in the middle is almost always done. So typically, the image power spectra are shown with low frequencies in the center, moving out towards higher frequencies and Nyquist in the corner. Computationally,
so in that case, in the center is low frequency, in the corner is high frequency after the shift.
That's really all there is to the 2D Fourier transform. What's tricky is figuring out how to map the features of an image onto locations in the 2D Fourier plane. And you know, when people teach the 2D Fourier transform, they typically jump immediately straight into showing power spectra of natural images. But I think it's better to start with really simple images and first to try to build a bit of intuition about how to interpret the 2D Fourier plane. Therefore,
So this is a very good video. I will give the link to in the Canvas. But this one, because I found this too late, so I didn't put it formally. But actually, there's some other video is I put as well. So this one give you all the theory for the derive the theory.
Different 2D DFT function. We can just
how
use
to
the 1D
how to
DFT
from 1D to get 2D FFT or DFT. Hello.
Actually, for those of you that took my
you can hear, right? Yeah. So yeah, this is a very good video for explain step by step, but this take quite a long time. You need to take a long time to learn. So this one give you MATLAB. You can just like learn what's the image, how to draw an image, and how to build an image, and the things step by step, and how to do FFT, and things. It's quite a nice video, but it's quite long. They give you they just like continuously talking about 1D and 2D connections, and then you will get the result, get the idea. So I hope like this video you just make this one as a dictionary. This video, the first video is dictionary. So first you just know the whole picture. Is that video I give you just played that video. Is give you a very good picture of the 2D FFT. But this one they give you the detail. So this is the first video, and the second video I put low pass filter. So low pass filter, I put a very simple low pass filter. Actually, they call the median filter. They just like average, like do an average. So
hello and welcome to the 11th session of Introduction to Image Processing using for noise removal and one
so
to the rest of the 8 neighbors. The median filter can be applied.
Introduce how to what's a 2D convolution. You know, like now you know the convolution neural network is very popular, right? It's now it's deep learning. It's fundamental. So you know, like CNN convolution neural network, they can do face recognition for with only around the, I mean, they have a 99%, over 99% accuracy. So their basic idea still use convolution, 3D, 2D convolution. So there's a media filter. They give you, teach you how to read a image and how to design a 2D filter. So this is a median filter, so just average. So this is a very simple, but we can, based on this simple one, you can learn how to design a filter for 2D filter. And this is high pass filter. This one is also very interesting one. they give you the calculation how to do the convolution and matrix calculation. They're very quick but very clear and very clear show. Because we don't have enough time, I just like jump to other part. But this 3 video and plus the first video I show you, I will put it in here later. So that's a very good video. You can learn. And some students maybe used to look at the slides. So I put the slides as well. So these slides first from 1D Fourier transform. You can see 1D Fourier transform. You already learned this one very well. So I don't want to discuss too much. So this is a calculator. This actually is something like frequency response equipment. And also this is a Fourier transform. You already learned. So we are concerned is how to extend it to 2D. So this still 1D. 1D you can see is one integration or one summation, but you can see they can extend it to 2D. There's a very lots of topic. This is 2D, two-dimensional. Two-dimensional you have for example, this signal is have X and Y. So for the image, for example, this 2D, X is in the horizontal and the Y is in the landscape. So you can find different position have different value. So F is the pixel, and X, Y is location. And then you can this is the like something like you remember for the Fourier transform transform is E minus J2 pi F, right? This one is E minus 2 pi U X and plus U Y. So you have used 2 pi F T. T is really relevant with X or Y, and F is relevant with U. So this time after you can do inverse as well. Well, after you do a Fourier transform, you have 2 parameters, and also you need to do if you discrete time, you need to two summation. That's some little difference. Just like this have a double integration and double summation, but for 1D is only one integration and one dimension integration and one summation. So you think about the difference. They also have, you can calculate the spectrum. This is a magnitude, and this is a phase. So you can draw the similarly. And also the calculation, I said, is very simple, right? It's just based on this formula. You can calculate. And now MATLAB is very powerful. They can directly calculate for you. And but the thing is how to explain the result. So this is some property, and they also have very similar property with 1D. So for example, 2D dimension is like and it's inverse. So they are doing just as I said, is doing 1D DFT for every row, and they get F, Y, and U. Y is still there. It's for one, but Y you first treat as constant, and then you just do X, and you get U. U is the one of the like frequency component. And then for example, this is the one picture. It's called fxy. And after you just do 1D Fourier transform, you get fuy like this way. And then you continue to do another to do column when you get the overall. So this is the procedure. So this is another example. This looks like something like a rectangular function, like because this one only have value in the square value. So maybe this because the bright one means very high value, and the white one is high value. The bright one is 0. So something like you can imagine. So this is something is a spectrum of 2D DFT. And you also think about the rotation. Rotation is actually something, if this one is a DFT is like this, if you rotate like that, so you get actually this one like phase changed. I will show you a MATLAB code to explain this kind of things. They can for example, they can linear combination. You have a because this 2D FT is 2D FFT, 2D DFT is also linear function, so they can directly do the superposition. I mean, plus them together, and then you can see you nearly plus them together, right? And also expansion. You can put some zeros, extra zeros, and that's still the same, looks the same. And you can this sine wave, some particular signal, very specific signal. So this one is a sine wave, but this sine wave is not have phase. So in that case, your 2 point is something like this. You can see this white point. So this, like, you remember for 1D, this impulse, right? For 2D is also like impulse, but they're because this is in the plane. So for the rectangular, this is like a reg function. So the reg function to the DFT. Can you hear me?
Yeah.
Yeah, that's good. So in that case, I look at this is a Gaussian function, something, and then this is it's DFT. So how to explain this one? This one is like for the Gaussian function, they are mainly for the low frequency component is have lots of components, because bright is the white one is high value, and impulse trend. This you still remember impulse trend for the 1D signal. So this 2D impulse trend, they also Fourier transform is still impulse trend as well. So later I will do the filtering, but we up to here Fourier transform. I show you a video. So this one. So you look at this left-hand side. Actually, this is a sinusoid, but you can see if you do maybe after finish I discuss with you. Maybe we look at this one first. This is the first one. You can see they have this is in the row. This is the column, right? So in the column, it doesn't change, right? The only row, row in the row, you can see the change. And this is sinusoid. So they have in that case, when you do a 2D image, you can see in most of area is 0. Only in the because you can see my arrow, right? The arrow.
Yeah.
Arrow. Yeah. So this part is corresponding to the change of the change of the frequency or change of the sinusoid. So we first look at the frequency change. The first figure is how to look at you observe the frequency change and the straight line change. So first we go there. So we can the frequency before was very small, and then you can see there's in the low frequency area, and later the frequency change big. What that mean? Frequency big. Frequency big means like they change slowly, change faster. That means you can see they change very fast, right? From the quicker, much quicker. So their frequency components go far. So in the middle is low frequency. In the edge is high frequency. So you look at it again, you will see. So this is from the video. I downloaded from that video there, and you can see that very soon. So you can see this one is before it's very close to the orange. So this is the second one. Second one is the phase change. The frequency not change, just like frequency. So the distance go to the 0 point is the same, but the frequency keep changing. Sorry, the phase keep changing. So in that case, this is rotation. So this is a looks like rotation. This phase you can see, you cannot see very clear. You also look at the first one. Do it see again. So the frequency is increasing. So you can see this one is go out. So make bigger, right?
Mm.
And then you go
So
to
why is it like pulsing in the amplitude one?
sorry, which one? Sorry.
In the amplitude spectrum,
Yeah,
you can see that it like pulses.
yeah.
Why does it do that?
No, you can see the color. Can you see the color?
Mm.
So the color means the bright color is have high value. So the blue is 0. So you can see the blue is 0.
Yeah.
Yeah. So you can see at start the high the color the higher value is in the middle, right? And then gradually change to the edge, to the side point, and that means this is high frequency.
Yes.
This is not impulse. This is a frequency domain. Frequency domain. You remember if you draw spectrum, the different colors tell the different value, magnitude, and the location. Because for spectrum they have a time and also have a frequency, right? But this one we have x and y. So in the x side is u and the y side is v. So they have a in the frequency domain, and then you looks like this one is just want to show you if sinusoid is in the row side changing, and then your frequency when frequency change, the high value point from will moving from 0 to the end. So maybe my explanation is not as good as the YouTube. I will show you the YouTube after the class, give the connection. But I just want to show you that this kind of basic idea. And now the second one, I want you first you look at this one. You can look at this one. You can see this is a high value. They go out, right? But like the changing is not that evenly because of the non-stationary property. This one is to show you when phase change, we frequency not change, and then what's the spectrum change. So they change like this way. And then the last one is like if the figure is like this, so you can see your magnitude doesn't change, and but your phase change. So that's some typical. You need to understand typically what's the 2D FFT and 2D spectrum, how to explain. So this is a example. After that, we will discuss about use you design filter, right? You will design, for example, low pass, high pass, the band pass filter. Like for example, we design low pass filter. There's some basic filter. For example, the low pass filter is make it more soft. You can see this one is low pass. Low pass filter. You can see this is the low pass filter looks like. So this is I told you like in the middle is a low frequency. In the edge is a high frequency. So high frequency is small, nearly 0, but low frequency is high. So this is a low pass. So high pass is the opposite. So high pass is in the middle is low, but in the edge is high. So you can see. So this low pass, this original one, this is low pass. So sorry, this is original one. So this is low pass, this is high pass. Low pass make it a blur, but the high pass will emphasize the edge. So but you need to find the balance. And also they have convolution, 2D convolution as well. Similar as the 1D, but they have a double integration and also double summation. So this one is even a future if you want to learn. And also you have a unit impulse, unit pulse as well. So they also have some other kind of function discussed for typical 2D function. So this is low pass. Low pass looks like this. I mean, this is some low ideal. This is called ideal low pass. You want to just like in the low frequency, just like it's 1, and the high frequency is 0. So this is an ideal one, but you never can get ideal filter. So this is some example. I will show you. Maybe use MATLAB. Actually, very easy to implement. Use MATLAB to implement the filtering. So high pass will make it more emphasize the edge, so the change fast component. Low pass will just like make it blur. So this is the example. This you can see from the eye. So if you use high pass, you can make it more clear in the edge. So they have other filters. So I put the example in the. So this high pass can make it more emphasize the edge. We look at, for example, the demonstration of low pass filter first. So low pass filter, for example, we have two. So you can maybe read the code. It's very easy, like only several line. You can do lots of things. So this read the image. So this is the image. I have two images. I read this woman picture first, and then I design. First, I have to do the DFT for the signal for the picture, and then I design the filter. So this is a cutover frequency. I can put it for different one, so we can have a different effect. For example, if I select the smaller one, and then the value, the picture result will look different. So this one is too low, so you very blur, but you can make it not that. So you nearly kill all of the components. So maybe you need to make it a little big. For example, this one. This one is cutover frequency is big. So it's low pass. The cutover frequency is big, and then it will be less blur. So less blur. It's just like looks younger. So this is some photo, and this also this is a design of low pass filter. So you can see only this figure. You can read the image. So it's just only this sentence. I put this one in the UTS online. Oh, sorry, in the Canvas already. So you can see also have a high pass filter. We also look at maybe we look at image, chest image. So this one, with high pass, we emphasize this is X-ray signal, X-ray image. So there's a neo inside the body. So you can see if you emphasize, and then it will become more clear. So we look at the original one. So this original one, not emphasize the edge, but maybe we can change the parameter as well, change the different cutover frequency. Maybe this is a very big cutover frequency. I make it if I make a smaller one. So you can see this is more clear. So you have other filter design technique. So just you deal with a 1D signal similarly as a 2D. So this is for the frequency analysis, 2D frequency analysis, and also for the filter design, high pass, low pass mainly. So this is a very good one. So I will show you. Hello, can you hear me?
Yeah.
Yeah, good. And then we go to the lecture 8. We look at. So I put the low pass demonstration, low pass and high pass, and the woman picture here. You can go to you can copy it in your computer. You can run this one to see low pass and high pass. And the FFT 2D FFT is also you can get some hint from this video. So very convenient. So I think when you learn this 2D signal processing, you maybe start from MATLAB. MATLAB is a very friendly environment to learn. So we look at next one is for this Carrie put some how to read the data. So this is a 2D filter, 2D wavelet transform. So 2D is wavelet. 2D wavelet can do two things. One is denoise, and also can compress an image. For example, you have a big size image. You want to make it small. You can use wavelet. Select different wavelet. But this is if you are 1D, you learn very well. I think you can start to consider about 2D. So this is also start from 1D, and then gradually.
Match what I.
So you still remember this DWT, right?
Something like this.
So actually, for 2D, we also have DWT.
LM.
So I only put this video. I think this video is quite long as well, and maybe you cannot fully understand. So my suggestion, when you read some video or learn something, you need to be careful. Although maybe I put something is maybe is useful, but maybe not suitable for you. My understanding is like, my thinking is like, if you 60% you know about this video, and then you can watch this video. But if less than 60%, you need to find some more video, more easy to understand video, and to learn. So for this video, maybe a little bit hard. If you never learn 1D wavelet before, I think this one is even harder. So if you have learned 1D and then you use this one, you turn to 2D, and you still maybe need some thinking and some other video or other book or other paper you need to read. But this one give you like again, it's like a dictionary. You can just understand the 2D wavelet. And also for this one, I put some student also used to use slides, so I put the slides. So FLIR and wavelet. So this one you already know for 1D. So this is multi-resolution. What's multi-resolution? I will show you later. Use 2D wavelet. Show you how to what's the resolution means. For 1D resolution is not that clear, but 2D resolution is very clear. What the resolution means? So it means like if you have a low resolution, you have your picture will become very unclear. So so basically you can use a wavelet to this can compress very complex image. So you can see, I will show you use MATLAB later. You can have a different resolution to get some image like this. This is a approximation. This is a detail, right? Details normally is high frequency component. You can see this is like a high pass, right? You get the edge clearly, right? But they still like 1D. You have a approximation and you have details. So you have but this one is a little different. Is like you need to do row and the column separately. First you have low pass and high pass for the row, for the row, and then you do high pass, low pass for the low pass, high pass for the column. This is a low pass, high pass. So in that case, most important signal is here. So this is a approximation, Fourier approximation of the original signal, and then this in the row is approximation, but in the column is detail. So this one is opposite. So but this one is less important. It's just this is all details, not important, but it's details. So this is a 2D DFT. I will show you how to use wavelet to do 2D denoise. You already know 1D denoise, right? 2D also can do denoise, and also you can 2D good thing you can also do compress image. If you have a very big size, you want to compress it, you can use this one. So this is a filter example, some filter. So this is the example. This is the one level of DFT. DWT. So this is the approximation, and this is in the row approximation, but in the column is details. So this all details. So you can now see the things, but they can do multiple level. So this is a theoretical what's the wavelet function. You still remember scaling function and also wavelet function. So this one is they can separate. Sometimes they cannot separate. So some wavelet they can separate, but most of the wavelet they can separate. This is a good property as well. This 2D wavelet decomposition we already discussed. You can continually to do decomposition, like continually to do several levels. So this is a 2D reconstruction. On the other hand, if you have this thing, and you can use several filter, you can get back, recover the image. So this give you some example. This is the original one. So you do several level of approximation. So you also use image processing by wavelet transform. So this is something denoise. This is denoise. So you can see make it more clear. So this one I want to show you. This one is very important. It's very useful. Wavelet image processing with MATLAB. MATLAB now is quite popular, quite powerful. But for this one, they teach you how to use there's one tools called integrated tool. For this one, you can try this one wave menu. If because I want to use this one to show you how to use wave menu, right? This one in the future version they maybe not appear. They put in the app. So you need to use app. They have a wavelet. They have lots of wavelet analyzer. They have similar wavelet analyzer. So I close one. I still go this way, but in the future maybe like so you can wavelet. You have 1D, 2D, 3D, even 3D wavelet. So actually, in this subject we also want to extend to 3D. But before our subject is mainly for postgraduate student. And also our teaching time is 4 hours. So now we only 3 hours, and we also together with a bachelor student and with undergraduate, both undergraduate student and postgraduate student. So we cannot cover all of these contents, but I hope you still in the future you are interested. You can try this. For example, 2D wavelet. You double click, and then you load the image. So I have image. I use maybe so many image, right? I have for example, I select the bone one, the skeleton one. So the skeleton one, and then they can see the DWT, and they can get this. I just showed you, and then they can inverse DWT can recover the image. So first we need to select what kind of wavelet we need. So for example, we use the Bayer, this one, and then we select 1.3 level. We can for different level. This up to 8. So with 8, and we analyze. So this is the like DWT still remember approximation and also detail, right? So for example, this is all detail. If you go there, you cannot see much. For example, you go to visualize. So this is the approximation. So it's all detail. So this is in the half detail. It's like this. So it's more clear in some sense, and also here visualize. So this is a high resolution, the highest resolution. But if you want to go low resolution, you go this way. So that's why they call it multi-resolution analysis. If you put here, if you visualize, you can see they have some tilt things. If you select more smaller, less low resolution, so the multi-resolution analysis, and then you can look still similar, but they use less memory because the pixels, they are very low. Yeah. So you go to here, if you visualize, so this one is, the block is bigger, right? If you very small, you can continue to do small, and also you can do a compress. Compress, you can, for example, first we'll do compress. And then I think this is okay for me. I just select, randomly select, and then I do the compress. But this compress is not very clear, right? But this if I save this one, you can see they will be very small. Save the image, save the compressed image. I maybe use JPEG. So this one cannot save the JPEG. So this one, maybe some issue is because this is this have some issue with because currently the software is upgrading, so some command cannot match very well. But I maybe select another called denoise. Another function is denoise, but normally it can be saved. For example, I change another photo. We close this one. So we do another one. We select, for example, this one. We do maybe just do a simple one like this, and then analyze. And you can see, so this is a detail. So this is in the if low. This is a low resolution. If we look at low resolution, this approximation of this one, but maybe this one will, if we compress, we will use less memory. So we will compress, and then we can save. So we can save, and then we can look at what's the the size will become smaller, of course, because you become blur. But this one you can do some change and tweak. Even no blur, still can use less memory. And I don't want to discuss too much in detail, but this one residual is like the details. So this is the details. You can see you can still see the person. Yeah, because it just emphasizes the each. We go stop here, and we go back to here. You can denoise. For example, I want to denoise. but maybe if you want to denoise, I need to select different, maybe different wavelet, and we have 8 level, and we do the denoise. So you can see, you can select different, different threshold method. So you have a, but anyway, they come back to hard. So you can see this denoised. I'm not sure it's better, but anyway, you can select different scale and use, for example, soft margin or soft one. So looks a little better. I'm not sure it's really better, but you can change different wavelet, different level of approximation. So it's very powerful, and then you can, based on these tools, learn to as a start for 2D image processing. So I cannot cover too much today. That's today's lecture, and I want to in the future, if you have a interest, you continue your study, and also you want to do some research in image processing, you can. Although currently, you know, like CNN, deep learning can do everything, like even for the image, all the image processing they can do, but they are mainly based on big data. They learn from examples. So you can think is learn from examples. Actually, human beings, if we ask, we don't know some knowledge. What we can learn, we can just learn from our experience. But if you want to truly understand your experience, you need to have knowledge. You need to have some philosophy and behind the things. Actually, the wavelet, the Fourier transform, and the things is actually a human already get the insight of this kind of phenomena. But you can use machine learning is mainly they just like, because they are computation power very strong, and then they just approximate anything. For example, for compress of an image, they also can use a convolution neural network. Convolution neural network, actually fundamental idea is they use convolution, and then but they can tune parameters and then implement the similar thing. So and also I have Python. I think Python is also powerful, can do the similar things, wavelet or signal processing. If you in the future you really want to go to deep learning side, and then you can after learn wavelet, I think you use wavelet and the Fourier transform, 2D wavelet and 2D Fourier transform, and as start, and then you go to complex things. So because we don't have enough time, I think today you all very anxious to do your project. So I stop for today's lecture. So that's all for today's for this subject, all the lectures. I hope you can learn something for signal processing, especially for biomedical signal processing. The only unfortunate is we cannot teach you hardware related things. But to be honest, the hardware is like an experience. In the future, if possible, maybe our school will find 1 day or 2 days open. Every student can go there. If you are in Australia, and then you can touch the equipment. Maybe in the future we will make some video to in the website, and you can from the video learn some equipment in our lab. Thank you so much for this semester with me, and we next we maybe Kari.
Yeah, I'm here.
Do you want to continue with your topic, because at least two group select EEG, right?
Yes.
Yeah, maybe you give more. Because they only have 1 week left.
Yeah.
So I want to you give some final hint to this group, and then Jeff, you give some final hint, because Jeff, you also have several group select ECG and ECG related. And I have one group maybe with me is for IMU, because only one group. I will discuss with them later. Actually, they are quite good as well, so I will maybe discuss individually. Now I make Kari as a host. I'm not sure this time is possible or not.